Hi, everybody. Welcome to your video lesson. Today, we are going to be talking about different types of bonds, and we're going to begin working with the word polarity. Now, before we get going today, just so you have some basic understanding, today's going to be a lot of vocabulary, lots of different terms, lots of overlap between the terms. It is not my goal for you to memorize and regurgitate all of these facts. So you are not learning these terms so that you could define them on a test. You are learning these terms so that you can use them accurately in a post lab write up. So, as we're going today, don't panic about the amount of words on a page. Our notes today are going to be mostly words, minimal drawings, not what you're used to. Again, the focus is to get a good understanding of these, to build essentially a dictionary so that you can reference these notes, use them later to successfully do a technical lab write up. So, as we're going, as I'm talking, and as you're starting to feel overwhelmed by the amount of new words, remember, you are not memorizing. You are aiming to be able to use your notes to understand and apply later. Now, before we get to the new stuff, let's review our old stuff. So we're looking at where are we currently at? Because we've done a lot of stuff and we've split that stuff over a semester. So where are we currently at? Well, we can look up elements on the periodic table. So we could look up the elements potassium and chlorine. And shooting you back to sheet one of the unit, we could look up those elements, we could find them on a table, and we could identify their valence electrons based on their position on the table. So, potassium, column one valence electron, one dot. Chlorine, column seven valence electrons, seven dots. We've been able to do that for a while. The next thing you were able to do was predict how these electrons moved. Now, we were not very picky about that so far. We're getting pickier going forward. But the potassium to chlorine setup would involve electrons moving between potassium to chlorine. You could draw that. You could identify ions from that. So, what would my ions be in this situation? Well, potassium gave up one electron, chlorine gained one electron. So my ions would be K plus 1 and Cl minus 1. This is a completed Lewis dot model, which would correlate to a ball and stick model. All right, keep it going. What could we do with those ions? We could cross and drop them to refer to the model as a formula, or refer to the compound as a formula, KCl. We could also name that formula scientifically as potassium chloride. And most recently, we could identify the mass of that formula. How would we do that? Well, we break it back up into its atoms, potassium and chlorine. This is a super simple one. There's no subscripts indicating I just have one of each atom. Multiply the quantity by the mass. Remember, the mass is always going to be to 2 decimals. So potassium is 39.098, which is actually going to round up to 39.1 or 39.10. Chlorine, 35.45. That is going to stay because the following numeral is a 2. So 35.45. Multiplying a number by 1 gives you that number. Oopsie. 35. 45. Once you've got the partial masses, we add them up to get a total mass of 74.55. And our unit here would be atomic mass units or AMUs. So this is where we're at. Where we're going. We are going to look extremely in depth at this, the electron transfer and the bond formed. We haven't looked that in depth yet. We've just said electrons move. When they move, they make a bond. For our purposes, all bonds have been treated the same. From here on out, we have 3 different types of bonds that we are going to be able to refer to. And these are going to be our 3 big vocabulary words for the second half of this unit. So the first type of bond is called a nonpolar covalent bond. And you might be wondering why I wrote that a little bit bigger. So these 3 terms are descriptive. They can tell us almost everything we need to know about the bond without writing the whole big paragraph. So breaking them down, the word nonpolar, non we know. Non means no or un. The word polar means charged. So nonpolar means uncharged. The word covalent refers to sharing. The word bond referencing that what have we done? We've moved electrons. So that's breaking down the term. Breaking it down a little farther. So why this type of bond occurs? Uncharged bonds with shared electrons occur when there is a small, which means less than 0.4, or no electronegativity difference between atoms. Okay, so what this means, small or no means small number. Electronegativity, this is how much an atom wants electrons. So a small difference would mean the elements involved in the bond equally want or don't want the electrons. So that's why it occurs. What it means. So since there's almost no difference, or there is no difference in the atom's tendency to take the electrons, they are going to equally share the electrons involved. So the electrons involved in bonding are equally shared. Since there is equal sharing, there is no charge differential created. So there are no charged regions. Since there are no charged regions, the substance is identified as a no or a low polarity substance. Now, the word polarity is kind of a stand in for magnetic. So, because there's no charged regions, these types of bonds are not magnetic. They're not attractive. They're kind of more like plastic. And if they were magnetic, they'd be real weak. Okay, so what are we looking at? An uncharged bond. Why do we get on uncharged bonds? Small electronegativity differences. Substances with this type of bond or traits of this bond. Substances with uncharged bonds tend to have very low melting and boiling points, which means it is easy or fast to change their phase. So essentially, if you wanted to take a liquid that is a nonpolar substance with a covalent bond, it would be extremely quick to boil on your stovetop. You could change the phase from liquid to gas exceptionally easily and exceptionally quickly. They tend to be poor electrical conductors, and this type of bond is insoluble, which means it won't dissolve, or the substance won't dissolve in water. Okay, so this is number one. Remember what I said? It's going to be a lot of vocabulary soup. The vocabulary is meant to be referenceable. So this is essentially our fact list for nonpolar covalent bonds. We've got two more bond types to cover. There's a lot of similarities, so you'll see some repetition throughout here. Our next type of bond is called a polar covalent bond. And we're going to break down this term using the breakdown from our previous term. So nonpolar meant uncharged. Non meaning un, polar meaning charged. Just polar here. So now we're talking about a charged bond. Covalent, still the same, still means sharing. Bond still means that we are referencing the movement of electrons. So now instead of talking about a charged bond or a charged scenario created by the sharing of electrons or an uncharged, we're going to be talking about a charged scenario created by the sharing of electrons. So why would this type of bond occur? So why would we get a polar versus a nonpolar bond? Well, nonpolar bonds formed when we had a small electronegativity difference. Polar bonds are going to form when we have a moderate or a medium electronegativity difference. And electronegativity differences are considered moderate if they are greater or equal to 0.4, but the difference is less than or equal to 1.7. So that's why it occurs. What it means: essentially, this means somebody wants the electrons more than somebody else. So the electrons are still going to be shared because that's in our definition, but they're going to be unequally shared. Along or on the bond. Because they are unequally shared, we are going to form some partially charged regions, which means this type of bond is going to have a magnetic trait. Not a strong magnet, but a moderate polarity, which is going to be like a medium strength magnet. So, since this is a similar type of bond but a little bit more extreme, our traits are going to be similar but a little bit more extreme. So, instead of low melting and boiling points, we are going to have medium or moderate melting and boiling points. Instead of these substances being easy or fast to change phase changes are going to be possible, but they're going to change, they're going to take time. So they're going to occur more slowly, they're going to need more energy. When these substances are dissolved in water, which they will do, these substances are soluble or dissolvable in water. They are going to create good conducting solutions, or they are going to be conductive in water. So all the same traits we had above, but a little bit more extreme because our bond is a little bit more extreme. We're still looking at electrons, but now instead of equally sharing electrons, we are unequally sharing those electrons. So for our third and final bond type, we're going to get more extreme again. We're going to look at very polar ionic bonds. Very polar Polar, we already talked about meant charged. So very polar is going to be very or fully charged. Ionic means transfer. And what did we transfer? Well, it's a bond, so we transfer electrons. Okay, so very polar ionic bonds. We've broken down the term. We're going to go through the same set of vocabulary now. So, why it occurs? Well, you should be able to make an inference. Polar bonds occurred because of moderate electronegativity differences. Very polar ionic bonds are going to occur because of large electronegativity differences. Large is going to mean the difference is bigger than 1.7 between the atoms. What this means for the bond. Well, instead of sharing electrons, now these electrons are being transferred, which means they're being moved between atoms or from one atom to another. What is this going to create? Well, instead of creating partially charged regions, now we're going to have fully charged ions. And our polarity is going to be very, very strong. It's in the name. Very polar is going to have a very high or a strong polar trait, which means these substances on a subatomic level are going to essentially be strong magnets. This type of bond is going to have very extreme traits. So instead of moderate boiling points and moderate melting points, we're going to see very high melting and boiling points. So these substances, because their melting and boiling points are so high, they're almost going to be exclusively solid at room temperature. Because those magnetic forces are so strong, they're going to be very difficult or resistant to phase change. It's going to take a lot of energy. They're going to be soluble still, which still means dissolvable in water. And when you dissolve them in water, the solution created is going to be an excellent conductor. Okay, that's our terms. That's our vocabulary. Now, you're probably wondering at this point what in the world we are going to do with this. Because what we've built today is essentially a page in a textbook. I've given you terms, I've given you criteria for those terms, and I've broken them down and given you some traits that go with it. Practice problems are going to look a little different because what we're practicing with is not a process. We're not practicing moving electrons. We're practicing understanding terms and applying vocabulary. So you're going to see some practice problems like the following. Match the model to the bond or to a bond type and justify your selection. I have intentionally left models out so far. I have given you no pictures to go with these terms because I want the pictures to be our practice. So I'm going to do three different models: Model A, Model B, and Model C. Model A, B, and C are each going to be simple ball and stick compounds. Two atoms bonded together. Yes, there is something different about C. Yes, that is intentional. For A, I'm going to use the color red to represent electrons. I am going to place 6 electrons close to the left atom or on the left atom, and then I'm going to place 2 more electrons kind of near the left atom. And then I'm going to put a symbol down below it. It's like an open infinity sign or an open figure 8. That symbol means partial. This atom on the left is partially negative. This atom on the left is partially positive. For B, I am going to place all of the electrons completely left justified. I'm going to identify the element on the left as a -1 ion, and I'm going to identify the element on the right as a +1 ion. For C, I am going to give each element 6 electrons. The 2 more electrons they need in order to complete their octet are going to be placed directly centered on the bond. I am going to indicate no charges. Okay, and now I'm going to match the model with the bond type. So I'm going to start with model A. And I'm going to use the same sentence structure for all of them. So model A depicts depicts I'm going to leave it blank, bond because. And now I'm going to analyze it further. So what am I looking at? Well, I'm looking at a bond where the electrons are closer to one side than the other. So that means I am looking at some level of sharing. When the electrons are on the bond, not on a specific atom, that indicates sharing. So these 2 electrons are on the bond. They are shared, but they are closer to the left. So they are unequally shared. Since we're looking at sharing, we're looking at our 2 covalent bond types. Nonpolar involved equal sharing. Polar involved unequal sharing. What do I see in my picture? I see unequal sharing. So this type of bond is going to be a polar covalent bond. How was I able to identify this? Well, I identified that the electrons, whoopsie, lights on a 30-minute timer. The electrons are unequally shared between atoms with, and then the symbol. This open figure eight is the symbol for partial. So I also have partially, because that's what this symbol means, charged regions indicated. This atom on the left has more of the electrons, so it's partially negative. This atom on the right has less of the electrons, so it is partially positive. So this is the type of practice problem you're going to get. Now, we're going to finish this problem together. We're going to use the same sentence guidance. So instead of model A, number 2 is going to be model B. Depicts a blank. We'll come back to that. Bond because. Okay, in model B, what am I looking at? Well, I'm looking at a more extreme version of A. Now, my electrons are all the way left justified. I am also looking at what you are used to looking at, which is full charges. This is a full -1. This is a full +1. What type of bond type is that? Well, that would be the last one we covered. Number 3, a very polar ionic bond. How was I able to identify that? Well, the electrons were transferred, aka stolen, by the left atom, creating fully charged -1 and +1, oopsie, ions. Okay, that leaves us with Model C, process of elimination. You should know where we're going with this, but we'll do it together anyway. Model C depicts a blank bond because ... Okay, so on C, what we are looking at is 2 electrons on the bond. They are drawn dead center of the bond, which means they are equally shared, which means we are our first bond type, nonpolar covalent. Articulating how I was able to identify this, well, first thing we notice, the electrons are equally shared. Drawn in the middle of the bond, and there's no pluses or minuses, not full ones, not partial ones, there's nothing. There are no charged regions are indicated. Now, coming back to letter C. So you might notice here I have 2 different colors used. On letter C, I use the same color. That's intentional. The most type, the most common way to get a non-polar covalent bond is when you're making something called a diatomic, which means you have 2 of the same atom bonded together. So this would be like the air you breathe, O2, or the gas you should not breathe, chlorine gas, because it would knock you out and kill you, Cl2. That's why I drew these the same color, because the most common way to get this type of bond is to have 2 of the exact same element bonded together. All right, so That's your notes. Lots of vocabulary, but your practice matches your note style. So use your notes to do your homework. Let me go ahead and pull your homework. Unit 5, second half. Okay. On your homework, it's a little different because your notes are a little different. You have been provided with a reading because I want you to practice using these terms. In order to get points for the reading, you need to highlight. In general, when I'm asking you to highlight, I want you to highlight about no more than 1/3 of the entire paragraph. So this paragraph is 1, 2, 3, 4, 5, 6, 7 lines. Don't highlight the equivalent of more than 2 full lines. I'm looking at the highlighting for evidence you actually read the thing. You guys know what the most important ideas are because I talked about them in the notes. The other way you get points for the reading is you need to annotate, which means you need to make notes in the margins. This is just a 1-page reading, so I'm looking for 5 notes off to the side. The notes don't need to be full sentences. Each note can be just 4 or 5 words. Your notes can also include models. So if you want to do drawings like this, that'd be great. That's the front. You're practicing interacting with these terms in a reading. You're getting points for highlighting and making notes on the page. On the back, you are using the notes I gave you and the reading I gave you to complete the sentences. Each term is going to be used exactly 1 time. At the bottom, you are using the notes I gave you and the reading I gave you to complete the table. You are going to be plugging in terms and numbers to these boxes. Your options are up above. So your 3 options for bond type are very polar ionic, polar covalent, and nonpolar covalent. You'll place one of each of them here. All right. So good luck. Complete your homework. And from here on out, keep your homework. So you are going to keep sheets 7, 8, and 9. Do not turn them in because these are going to be a big helper to you on your last lab. So complete your homework, but keep your